I buchi neri sono una delle forze più distruttive della natura, ma gli scienziati credono che siano la chiave per capire uno dei misteri più importanti: da dove viene l'universo. Il problema è che più cerchiamo di studiarli, più ci sembrano strani. Infatti sono praticamente invisibili e si trovano a miliardi di chilometri dalla Terra. Ma qualcuno ha trovato il modo di studiare i buchi neri qui sulla Terra, utilizzando una vasca e 200 litri d'acqua. Siamo alla Sissa di Trieste, la scuola internazionale superiore di studi avanzati. È la casa di 400 ricercatori che lavorano tra matematica, fisica e neuroscienze. Uno di questi è Silke Weifurtner, che ha messo in piedi un esperimento unico nel suo genere. Ci permetterà di vedere un buco nero.
So in general that is an analog gravity experiment, which means that you try to mimic some effects that occur in our universe in a tabletop experiment. So in particular in this experiment we're interested in setting up an artificial black hole, and in more detail we're setting up a rotating black hole.
L'esperimento è il risultato di una collaborazione tra la Sissa, il Centro Internazionale di Fisica Teorica e il Centro di Ricerca Elettra.
We're at the Elettra Synchrotron Laboratory. This is where the laboratory, fluid dynamics laboratory of the International Center for Theoretical Physics is housed. This is part of a scientific agreement that we have with the synchrotron.
Il laboratorio guidato da Joseph Nimella è specializzato in fluidodinamica, ma ora ospita anche un esperimento su modelli analoghi di gravità. Ma cosa c'entrano i buchi neri con la fluidodinamica? I buchi neri sono oggetti estremamente affascinanti, ma sono anche molto estremi, tanto che nessuno ha una loro esperienza diretta. Da qui è nata la necessità di rappresentare i buchi neri tramite dei modelli. In questo esperimento, per esempio, l'analogo è lo scarico della vostra vasca da bagno e lo studio del buco nero analogo si fa tramite fluidodinamica.
What is nice about these experiments are relatively simple. So we're looking at water flows, open channel flows, bathtub vortex flows. So very, very hands-on systems. And of course they kind of lay the foundations to look into more involved or difficult or complex systems such as superfluids. At the moment, over the last few years, this whole field has just come to life. So before it was more theoretical studies which would dominate analog gravity studies. Now it is actually the experiment. So there are, let's say, 2 or 3 successful or promising experiments there at the moment, but all over the world in different systems people started to investigate questions like Hawking radiation, superradiance, cosmological particle reduction. And what we benefit from this is, of course, we change our understanding of quantum field theory and curved spacetime. We get a hands-on approach experience, which also helps us to understand how difficult would it be to detect such an experiment in real life.
L'apparato sperimentale, disegnato appositamente per l'occasione, è in base composto da una grande vasca con un foro al centro.
Essentially, the nice way to think about our experiment is that it acts like a very large bathtub. So the vortex that forms in the center here is very, very similar to the vortex that forms above the drain in your bathtub. Hence the name for this fluid dynamical phenomenon, bathtub vortex flows. Our experimental setup is 3 meters long, 1.5 meters wide, and 1/2 meter deep. What we do is we pump water out of our reservoir located beneath the tank. The water is pumped in through 2 inlet arms located on opposite ends of the tank. The rate of water that we pump into the tank is at about 6,000 liters an hour.
Sul lato della vasca è posizionato un generatore di onde e quello che si vuole analizzare nell'esperimento è proprio cosa succede all'onda quando incontra il vortice. La teoria dei buchi neri rotanti prevede infatti un effetto particolare chiamato superradianza.
So in this experiment in particular, we send a long wavelength water wave towards our bathtub vortex, our analog black hole. In the end, we expect that the amplitude of the reflected wave will be greater than the amplitude of the incident one. And if this really happens, if we can measure that, then it will correspond to the extraction of rotational energy from the black hole, and it will mean that superradiance has occurred.
Per studiare l'effetto della superradianza in questo modello analogo, sull'acqua viene proiettata una griglia. Guardando come la griglia viene distorta, si può risalire all'onda che è passata sulla superficie dell'acqua.
The method we are using to measure the height of the full water surface at once is actually easy to imagine. Just picture yourself in a cinema watching a movie, and now somebody pushes against the screen from behind, deforming it, so the movie also gets distorted. Now in our case, the screen is just the water surface, and the movie we are projecting is a still image of stripes. We are recording the distortion of that stripes from above that are caused by water waves traveling in a tank. And from that distortion, we can then reconstruct, using some software that we made, the original waves that caused it. So that's the basic principle. Now, the interesting part here is to get a very high accuracy that we want to have, and that's one of the things we are currently working on.
All'esperimento hanno collaborato molte persone con competenze diverse, dalla fluidodinamica alla cosmologia.
So this experiment is actually a nice example of an interdisciplinary experiment in the sense that we require various institutions and various people, scientists with different skills, to be involved. This takes place in a fluid dynamics laboratory because the centerpiece is actually a vortex flow, so we need a laboratory in which we can create that, which has that space. We need some expertise in fluid dynamics. It also involves simulating processes which occur around a black hole, and for that reason we need the astrophysics expertise at CISA. So this is a real collaboration between CISA and the ICTP. We also have a collaboration with Elettra, as you see here. Elettra plays a very significant role in helping us actually realize this. There's also the University of Trieste. And what do we get from the University of Trieste? We get students, and students are really the vital resource for this project.
Per ora, i misteri dell'universo rimangono ancora nascosti. I ricercatori, infatti, stanno ancora calibrando l'apparato e i metodi di analisi dei dati. Quello che è certo è che i risultati non ci diranno solo qualcosa in più sui buchi neri, ma anche sugli aspetti di fluidodinamica.
This is a very interesting flow behavior. So we also want to investigate some of the fluid dynamical aspects of this setup. So at the end of the day, we want to also show perhaps that, once again, that a collaboration between people working on different areas in physics, that if you set up such a multidisciplinary research team, that a lot of interesting results will come out at the end.